So, for example, new slide. For example, here's my system of equations, and I want to find a general solution. Find a general solution. X1 prime, not vector. I'm writing this without matrices first. We'll turn it into a matrix. So X1 prime equals 3x1 plus 4x2. Function x2 prime equals 3x1 plus 2x2. So we want to find a general solution. Function x1 prime equals 3x1 plus 4x2. Function x2 prime equals 3x1 plus 2x2. We got to do a couple of checks before we can make sure that we can use this method. 3x1 plus 4x2, 3x1 plus 2x2. Got to do a couple of checks before we can do this method. First of all, needs to be a homogeneous system of equations. Give me a thumbs up. Is this a homogeneous system of equations? Are we good to go there? Yes, nodding, yes, cool. Okay, second, needs to have constant coefficients. Does this have constant coefficients? Are we good to go on that front also? Constant coefficients. Yes, good, happy, yes, 3, 4, 3, 2, constant coefficients. All right, so this is homogeneous. That's your check that you need. Homogeneous with constant coefficients. We need both of those. Homogeneous with constant coefficients. All right, so my matrix A, reading across, is 3, 4, 3, 2. There's my matrix A, reading across. Okay, so the equation that I need to solve is determinant of lambda I minus A equals 0. That's my equation that I need to solve. Determinant of lambda I minus A equals 0. So 0 is going to need to be the determinant of, I'm going to write out all the steps the first time, and then the second example will short circuit a little bit of these. Lambda times the matrix 1, 0, 0, 1 minus the matrix 3, 4, 3, 2, right? Lambda I minus A. People who have taken linear algebra, this is again a step where you can jump ahead of me if you want, and you can go get coffee or something. The advantage of teaching class and being in your homes. So this is going to turn into determinant of lambda 0, 0, lambda minus 3, 4, 3, 2. There's my determinant. All right. And then we'll go up here because I'm going to run out of room. So this is the determinant of lambda minus 3, negative 4, negative 3, lambda minus 2. Determinant of this, lambda minus 3, negative 4, negative 3, lambda minus 2. We know how to take a determinant of a 2 by 2 matrix, no problem. So this is lambda minus 3, lambda minus 2, minus 12. Lambda minus 3, lambda minus 2, minus 12. This is supposed to be equal to 0, so I'm going to need to do some foiling and combining. So lambda squared minus 5 lambda plus 6 minus 12. Foil out. Lambda squared minus 5 lambda plus 6 minus 12. And if I factor, this is lambda minus 6, lambda plus 1. Lambda minus 6 times lambda plus 1. Doesn't matter which is which, so let's go with lambda 1 equals negative 1 and lambda 2 equals 6. So lambda 1 equals negative 1 and lambda 2 equals 6. Everybody good? You've just found the eigenvalues. You've gotten through week 2 in linear algebra. Actually, that's not true. Eigenvalues come way later in the semester, but you can find the eigenvalues now. Good? Finding eigenvalues? All right, let's go back to the previous slide. So the other thing that we have to find, we found our values of lambda I. The other thing that we have to find is these associated eigenvectors. That's the other thing that we have to find in this case, associated eigenvectors. So I'm going to need to look at 2 of these because I've got 2 eigenvalues, so I got to do this twice. Once again, my matrix A, if I copy this down, is 3, 4, 3, 2. Lambda 1 was negative 1, and lambda 2 is 6. So now I got to find the eigenvalues, or eigenvectors for these. So for lambda 1 equals -1, I need AV equals lambda 1V. That's what I need. Or in other words, 3, 4, 3, 2 times the vector V1, V2 equals -1 times the vector V1, V2, right? I don't know what V is, so this is going to be my unknown vector. 3, 4, 3, 2 times V1, V2 equals -1, V1, V2. I can multiply out. So I am going to have 3V1 plus 4V2 and 3V1 plus 2V2 on the left-hand side. And this needs to equal -V1, -V2 on the right-hand side. Okay. We can rearrange, and I'm going to turn this into a system of equations. So adding each of these pieces, taking each of those over to the left-hand side, I'm going to get 4V1 plus 4V2 equals 0, and 3V1 plus 3V2 equals 0. That's my system of equations that I need to solve. Everybody clear on why that's my system of equations that I need to solve? All good? Okay. I am going to do this with an augmented matrix because we're going to need to do this for 3 by 3 in some of the homework problems, and we want to make this as systematic as we possibly can. So I know that this is just 2 variables and 2 unknowns. It would be easy to do, but let's do it with an augmented matrix just to get that process down. So 4, 4, 3, 3, and then my augmented part is 0, 0. And in this case, my column headings are V1, V2, and right-hand side. 4, 4, 0, 3, 3, 0, and my column headings are V1, V2, right-hand side. The only entry that I need to zero out is this 3 in the bottom right-hand corner to make it triangular, right? So that's going to be -3/4 times row 1 plus row 2 gets sent to row 2. -3/4 row 1 plus row 2 gets sent to row 2. If I do that, the matrix is going to turn into 4, 4, 0, and then all zeros on the bottom. 4, 4, 0, and all zeros on the bottom. Let's turn that back into an equation. So 4V1 plus 4V2 equals 0, and 0V1 plus 0V2 equals 0. That second equation isn't helpful. It's always true, which is good, but that second equation isn't helpful. So fancy math word, what we have is a dependent system of equations. People who have taken linear algebra should remember that word, dependent and consistent system of equations. So we can pick any answer that we want. It doesn't matter. Any answer is going to work here. So we can say choose, sorry, something's up with my pen. Choose, there we go. V1 equals, I don't know, I don't really care. 1, why not? And then V2, if you solve this, is going to have to equal -1, right? So if I pick V1 to be 1, then V2 equals -1. The only restriction is that you can't choose something so that your vector V is equal to 0. That's your only restriction. Otherwise, you have problems with linear independence. So in this case, my vector V is the vector 1, -1, right? That's my vector V. And then my solution, x1, we'll call this V1 because it goes with x, is V1 e to the lambda 1t, right? That's my solution. That's what it's going to look like. So this is going to be 1, -1 e to the -1t, 1, -1 e to the -1t. Or if you want to multiply it and take that e to the -t inside, e to the -t, negative e to the -t. Doing okay? All right, I still got to repeat this process for lambda 2 equals 6, but I want to show you a shortcut for that. So we're good so far? Everybody's good? All right. Okay, shortcut. So the matrix that we got looked like this up here, right? Once we plugged in, we got 4, 4, 0, 3, 3, 0. Once we plugged in, that was our matrix that we got, right? Go back. I wish this were all on the same chalkboard, and it's not. Go back to your determinant matrix right here. If you plug in lambda 1 equals -1, you are going to get the same matrix, almost. So the only difference is going to be that everything's negative instead of positive, right? If you plug in lambda equals -1, you're going to get the same matrix almost. The reason that everything is negative instead of positive is because I took the negative V1, negative V2 over to this side of the equation. I could have just as easily taken all of this over to the right-hand side. It doesn't matter. You're still going to get the same answer either way. So therefore, instead of going through this step and this step and this step, you can jump right to this step by plugging in lambda 1 equals -1. You can totally jump right there. And that is what we are going to do with the lambda 2 equals 6. That'll make our life way easier. So we can jump in and plug right there. All right, so let's do the lambda 2 equals 6. Remember that my matrix that I had was lambda minus 3, -4, -3, lambda minus 2. That was my matrix that I had, right? The determinant of that's my matrix. So therefore, here's what I need. I need 6 minus 3, -4, -3, 6 minus 2, and then I'm going to add the augmented part with zeros as well. So 6 minus 3, -4, -3, 6 minus 2, and 0, 0. Not too bad. 3, -4, 0, -3, 4, 0. Need to zero out the -3 down here. We can do that with row 1 plus row 2. Get sent to row 2. That'll help me zero out that -3. So I'm going to get 3, -4, 0, 0, 0, 0. I'm not going to write the second equation with all the zeros. All I need is 3v1 minus 4v2 equals 0. Okay. And we can choose, I would like to avoid fractions. So let's choose V1 to be equal to 4, and then V2 has to be equal to 3. There's nothing wrong with choosing V1 equals 1, but then I'm going to have fractions and I would rather avoid those. So in this case, my vector V2 is 4, 3, and my vector X2 is 4, 3 times e to the 6t, because I am dealing with lambda 2 equals 6 for this particular example. If you want to multiply through, 4e to the 6t, 3e to the 6t. Yay, final answer. So final answer, x is c1 vector x1 plus c2 vector x2. So this is going to be c1 times, sorry, going back a slide, e to the negative t, negative e to the negative t, plus c2 times 4e to the 6t, 3e to the 6t. So that's your general solution for your vector x. You can also write that as functions x1 of t, x2 of t. So you could say, or x1 of t, not a vector, just a function, c1 e to the negative t plus 4c2 e to the 6t, right? That's that first row, if I combine those all into a single vector. And then x2 of t is negative c1 e to the negative t plus 3c2 e to the 6t. I want you to get comfortable writing it both ways. I don't care which way you're going to write it. It doesn't matter. That's okay, either one, but I want you to be comfortable with both. Also, we did some choosing, right? We chose the coefficients 4, 3. We chose the coefficients 1, -1 on the other side. So your answer might look different from the back of the book if you choose different coefficients. That's okay. That's totally fine. Answers are equivalent. The answer will change in the C1 and C2. That's where the answer comes in. But just be aware that your answer might look different than in the back of the book, and that is fine. Okay.